We'll go ahead and start. So I already said hello. This is what we're going to try to do here. Anthony's been bugging me for a year to talk about satellites, and I've been stiff arming him, and we didn't really have a system up here until now, until the last few months. So really wasn't anything to say. But I'm going to kind of talk about. Let me back up a bit. The subject of satellite comm with amateur radio is many hours of discussion. So I'm not going to cover all of it. Certain aspects I could cover an hour just in themselves. What I'm going to talk about is basically just our club, how we're going to use it, that kind of thing. So starting with the overview of why. Purpose, I'm talking about the basic satellite, mostly just descriptions and some terminology. I'm talking about our system, how we're going to operate it, and what our future plans are. So we'll start with Keith Pugh. He was a big AMSAT, ARIS member. He belonged to all those organizations. He traveled to all the different conventions. He had a couple satellite stations built at his house. He was big into this thing. He's also big into regular amateur radio also. That Flex radio is his. In 2017 or so, he proposed a club that we build a ground station here with the purpose of getting to the point where we could do when he gets to we'd be able to get the video downfeed from the ISS. That was his big goal. Unfortunately, in 2018, the transmitter died. And in 2019, Keith passed away. So this project's been on the back burner ever since then. Nobody in this club knew how to do satellite stuff. So it took a while to get momentum going. What we want to do with this system is by having a permanent system in place, we can train users and eventually use those users to do school contacts and that kind of thing. And that was, again, Keith's big thing was to do IRS school contacts. So it's hard to train people using satellite if you don't have a permanent station. We have a portable station we do for field data. That takes a couple hours to put up. So we really can't generate a class on that. By having a permanent station here, we can just work on it anytime we want. And finally, I want to do that digital amateur television coming out the ISS. That's the purpose of this whole system. I'm going to go over some basics, some terminology, that kind of thing. Start with uplink, downlink. With repeaters, you talk about transmit and receive frequency. The satellite, we talk about uplink, downlink. Downlink is what the satellite is sending down to Earth. Uplink is what we're sending up to the satellite. Pretty simple. It's the same exact thing as repeater, but we use different terms. Our system is going to do VHF, UHF, FM, and linear satellites. I'm going to talk about those frequency parts a little bit later, but that's the limit of what our system can cover. And I'll talk about those frequencies later on. Another issue is satellite power output. I'll kind of show an example here in a second, but we have to have high gain antennas, good coax, because the satellites themselves don't put out much power. And we have to have an antenna aimed at them to get the best signal. And finally, let's talk about AOS, LOS. That's acquisition signal, loss of signal. They're theoretical terms the way we use them. But essentially, when the satellite is overhead, its footprint, we're under it, that's considered AOS or acquisition signal. And when it passes away, passes below the horizon for us, that's loss of signal. In reality, it's a much smaller window than that because we have to be able to hear it to be real AOS. However, the software just determines that when it becomes above the horizon, that's considered their AOS for active purposes. So here's an example of one of the CubeSats, the Saudi sat. You can see it's a 250 milliwatt satellite. So that's why we need high gain antennas and low loss coax. Very low power coming out that satellite. It does have altitude, which I'll talk about in a second. It's an FM satellite, one of the two choices of FM or a sideband. So I got a busy picture here, but I want to demonstrate what we're talking about with satellite orbits real quick. If you look at the horizontal axis, it's distance. One's from the center of the Earth, one's from the surface. And the vertical axis orbital period is the top. That's how long it takes to make one revolution around the Earth. And then speed, just for a fun number. If you look at the farthest outside ring, as far as this outside ring, that's the geostationary orbits. The geostationaries are, as far as we're concerned, they're not moving, but they are traveling. We just have you traveling the same speed that it's traveling. If you go in from there, and they're 22,500 miles. We go in from there, you can see where the GPS satellites are, and obviously because they're not geostationary orbits, they're actually traveling. They're in an orbit. Get in further, and now we're in the low Earth orbit satellites, including the ISS, Hubble, etc., and all the amateur satellites will be operating. And that's all within 1,000 miles. Roughly, it's about 1,500 miles in, but most, I think, the stuff we work is about 800 miles. The Starlinks go all the way up to 1,500 miles, so they're kind of all over the place, but it's still considered low Earth orbit. Another thing to look at, up here you got the orbital period, so how long it takes to make a revolution. We look down here where the low Earth satellites are, about 45 minutes or so. So it's going to pass every 45 minutes because it's traveling really, really fast. And you only get about 15 minutes maximum between horizon to horizon. So now we've already talked about this theoretical AOS, LOS time. So now you can see that our actual time may be 10 to 12 minutes at best. We can actually talk to it. I just brought this slide up just so I can show you some of those things I'm talking about. So first off, we look at this highlighted circle. This piece of software shows that is the theoretical AOS, LOS. So within that highlighted circle, we are inside the footprint of the satellite, and in perfect conditions, we'd be able to contact it. And of course, hear ourselves. The arrow in the software shows what direction it's going. The dotted lines, the dots are showing the future orbit. So if you look where it is right now, you see where the future orbit is. So every orbit steps over a little bit, and that little bit just depends on the type of orbit it has. But you can see, just kind of guessing, that we actually would have had two passes with this satellite. One when it first passed up here, and now this one it passes here. This yellow line here, that is actually the sun line. That's important because some of the satellites don't have good enough batteries anymore, and they can't operate in eclipse or in the darkness. So if they're behind the sun, they're not going to be turned on. They just automatically turn themselves off. Up here, that's just another satellite. So that's showing its orbits real high up there in the north part. So ignore that one. Now I'm going to talk about the system we built here. I'm basically going to start from the bottom to the top with the radio room, the wiring involved, the preamps we have to boost that signal, our rotor, including the whole mass assembly, and then the antennas on top of it. Start the radio room. We have to control the radio and the rotor system. So we have a piece of software called SAT-PC32. There are many choices of software out there. This one works on Windows. I'd say it's kind of the go-to solution. So that's the one we're going to use. That's what I'm going to talk about. If someone wants to use their own software, that's fine. The rotor controller is a Green Heron RT21. I'll show a picture of these things, talk a little bit more in a second. And then the radio's ICOM IC9700. So the rotor controller, Green Heron RT21 as L, so azimuth elevation. If you notice, it looks exactly like the one sitting on top of the Flex radio because this is two of them in one box. So it's two controller boards in one box. So you've got two USB ports, two everything else. But you got a display, you've got up here, it's a bad slide. Up here is our elevation display, our elevation knob, azimuth display, and the azimuth knob. A lot of satellite users will set their equipment to around 0 to 90 because they don't want to deal with the wiring and a few other things. We have ours to do a full 180 flip just because it's quicker to make the transition once it reaches its azimuth limits. So if it reaches all the way around here, it could just flip up and over rather than having to spin all the way around the other way to catch it. So now it goes 0 to 180. The rotor itself has limit switches at 0 to 180. It doesn't affect us. It just won't physically go past that. However, if you're watching the rotor and it's at those limits, it may give a no motion warning just because The limit switch simply stopped it. That's all that means. Now for azimuth, you got two rings of numbers on there. And you can see 180 is at the top and then 0 below that. That's so you can determine which way you want to point the center of the satellite. So ours are the antenna. Ours is set up so north is the center. So it'll go 180 to the left or 180 to the right. You could do it the other way around. It's kind of just a user option, I guess. So if we're manually tuning it, you're going to use the inner circle of numbers. Now for rotation, there are no limit switches. This box itself limits it. So if the box has a problem, it gets a bad power or something happens to it, it could lose its memories. It's pretty hardy. It shouldn't happen. But that's why we have to monitor the satellite while we're working it and make sure it's doing what we think it's doing. Otherwise, the last person yanks off the coax and busts the antennas has to fix it. Now I'll talk about the radio. The club just bought this because it has all the bells and whistles. We had Keith's old radio. It was really getting old and it had some limitations. Talk about a couple things. It is a VHF UHF radio, although it does show 1.2 gigahertz also. We're not using that function. We don't have any 1.2 gigahertz satellites right now. If we do, we could add another chunk of antenna and run a coax for that. But right now, just running UHF, VHF, 7 centimeter, 2 meter. It's an all-mode transceiver, so it does FM, it does sideband, CW, etc. It is a full duplex radio, which means as you're transmitting, you're simultaneously receiving, which is important for finding yourself on the satellite. And of course, it's got a real cool spectrum display, so you can see where exactly your signal is coming back down on. I think it's 100 watts on one of the bands. I don't remember which one it is. I think 70 on UHF, something like that. Most satellites, we're going to run low power on it, maybe 20 watts, unless you're really at the fringe of it, just because they try to put out the same amount of power that came into them, and you can actually just use up their batteries. They try hard to get that signal out. Oh, one more thing. So the standard setup for AMSAT radios is you'll have the downlink at the top frequency. So this will be the downlink frequency. So that's what the satellite is sending down, right? The satellite's above us. Top one is the one it's sending. Uplink is on the bottom. That's us here down the bottom. This radio is actually not showing that because the TX should be down here the way we're operating. So again, that's another thing. When you're setting the stuff up and you look at the radio, make sure you have the correct transmit set. Otherwise, you're not going to be very happy with the results. All right. So let's talk about the wiring. Again, I talked about we need as little loss as possible. So we invested in LMR 600, from the radio room up to the doghouse. And the doghouse is a little ventilation shaft above the roof, right about up there. So it goes up there, and in that ventilation shaft, we have surge protectors. And then from there, it goes out to the preamp box.
I'm sorry, what is the LMR 600 again?
Coax.
Oh,
Yeah.
What gauge was coax?
LMR 600. It's hard. It's about this big around.
I thought like gauge wire.
No.
the 600, it says it's 6/10 of the engine diameter, so it's a little bit over a half inch.
Yeah, this is what we can afford. It'd be nice to have 1 3/4 hardline, but nobody in the club seemed to want to donate any of that. So, come on in, Tom.
Found you.
We started without you. Sorry.
Okay.
I'm only up to the wiring anyway. You have plenty of time to critique me.
We're from Dallas County, you'll be aware.
Come on in.
That sound like dish.
We'll get to that. We have LMR 400 from the preamp box up to the antennas, LMR 400 Ultraflex, because it needs to be able to move as the antenna swings around. And we also have a short chuck of LMR 400 from the radio to the LMR 600 for the same reason. LMR 600 doesn't want to bend less than about this big of a circle. So it's low loss, but it's hard to play with. To control the rotor, we've got wiring running from the rotor all the way up against the doghouse. And again, we have a surge protector for the rotor wires, so we don't blow everything up. And then from there, it goes straight up to the rotor itself. We've done some pre-wiring for antenna polarity switch. Both antennas have polarity switches, and I'll talk about that. We pre-run some coax for that, and we use coax as a technique because you're going to run them parallel to the coax to the antennas because the switch is right on the antenna. So in order to avoid some crosstalk or other problems, you just have a shielded coax as your switch power. And then we pre-ran some coax for the digital enter TV downfield. Let me talk about the preamp box. It's kind of one of the key parts of this. We have high gain antennas, we have good coax. The preamps, I was going to look it up and I forgot. I think they're 10 dB preamps, but they are advanced receiver research preamps. The club actually has like 8 of these things at various locations for various purposes, just for satellite stuff, but we've just acquired them, I think 3 or 4K from Keith. There's one is 70 centimeter, one's 2 meter. They, like I said, I think they're 10 dB gain, but I'd have to look it up. They have the capability to accept power through a plug right here, and there's some reasons you'd want to run wire up there and remote switch it. The preamps themselves, if they sense and transmit a signal, they will bypass themselves, so they won't blow up if you're transmitting through them. We don't rely on that. You can also get them with the option to run off bias T or off coax power from the radio. That ICOM 9700 will send about 12 volts to the coax, and our preamps were set by the factory to be powered off that coax. So that's how we're operating. When we're not transmitting, they're being powered by the radio. As soon as you hit the mic button, the radio stops sending power to them, and they automatically go into bypass mode. In addition, we're running, as a technique, we're running a duplexer to filter 2 meter signals. We do best practice as we can. We've got a wide boom, we've got the antennas as far apart as they can be, but there is a possibility that you can transmit on your VHF antenna. It'll be received by the UHF antenna and then run through the preamp, and now you've blocked out anything coming down from the satellite. So, and we call those satellites are called Mode J. They transmit, or their downlink is UHF. So they're more susceptible than other ones. So how it works is we simply run the UHF, right, 70 centimeter coax straight from the antenna into the entrance. We run the, I think it's this line, the 70 centimeter out into the preamp, and then we just let the VHF dangle. We don't terminate, we just let it sit. And that's an AMSAT approved solution for, it's called Mode J DSense, I think is what they call it. Believe it or not, I don't have a picture of our box for some reason, but I stole, I'll tell you who this is later on, but I stole the plans. I stole the plans from this one. So I took this picture, and it has the same preamps, and so I know how big the preamps were. I laid it all out to figure out how big the box was, and I bought an identical sized box. So I totally copied them, except for they're running, like I said, power to the preamps directly for their setup. But they do have that duplexer DSense in the wiring. So ours looks just like this. I think our box is a bit wider, but same idea. We've got coax coming in from the antennas and coax going out to the club radio room.
Is that a metal box?
Yeah. Water sealed and all that. This is kind of a cat's eye view of the antenna. David Darcy was doing tower work and took a picture. But you can see here's where the box is, right there, about halfway up the mast. We spent a lot of time with it sitting out here trying to figure out where to put the preamp box and to run a coax so that we could get full swing without it dragging on the floor or twisting up. So it took a few days to get the position. And once we did, we marked it, and that's where it's going to sit. I'll talk a bit about that later. Which is the segue to the rotor system, right? So it includes the mount and mass, which is it's a Roan JRM 238 non-penetrating roof mount with a 10-foot mast. Non-penetrating roof mount means we're not drilling any holes. It's not permanently mounted to the roof. It's just sitting there. Roan is the company. JRM is the style. It just has one ring for ballast on it, it's a smaller one. But I think if Dallas Cliff did the math on it, that's where I got the numbers that this would work for us. And the 238 is 2 3/8 inch mast diameter. That's the biggest that our rotor will actually mount to. The rotor itself is an SPID, RAS, ASL. I think it's 1 degree precision. I believe they have a 1/2 degree one. It's called a high something. This should be good enough for us. Keith bought this rotor. It weighs about 50 pounds, and I think it costs like $1,000 or something with the controller. And we have 11-foot fiberglass crossboom we bought new for this project. It has a center section of 2 feet as an aluminum shaft, so you can really clamp it into the rotor itself. And then the tube is it's hollow fiberglass tube. It's really thick walled, so you get a good clamp on the antennas. And here's Walter and Mike demonstrating one purpose of the ballast. But if you look, probably can't see down the bottom, but there's a rubber mat that this thing's sitting on. So the rubber mat covers the whole base of this. Obviously the mount sits on top of that, and we have 500 pounds of ballast on top of the mount. It should keep it from skidding as well as tipping, and it hasn't moved since it's been up there, so something must be right. And I can see Mike do his best Vanna White demonstrating the second half of the mast, so that's the full 10-foot height. The rotor's on top of it, that big brick right there, and then there's our 11-foot crossboom. And that's Sam right there helping steady the ladder, and then the preamp box is right tucked in there.
I missed quite an integer actually.
That's the next slide.
Oh, it's an
What timing? Thanks, Tom. So we're running M2 antennas. We're actually using Keith's old antennas that he had in his system, but he bought a brand new set for the club to use in our system. We still have the new ones in a box, storage. We're just using his old ones because they're working, and at some point later on, we decided we needed to build them, then I guess we'll build them. But for now, we're running the old ones. They're approximately 13 dB, and they're approximately 10 foot long. I say approximately because one's a little bit more, one's a little bit less, both length and decibels gain. They are circular polarized from the factory, and the polarization reversal switch built onto them. I think that's actually an option, but that's built onto them. So I think normally it's right-hand circular polarized. You flick the switch, and it goes to left hand. That's to, if you have audio problems, start losing the signal, you switch polarity. And that's what our pre-wiring has done that I haven't hooked up yet. And there's the full setup all made. This is obviously the UHF, the bigger elements. And there again, you got Mike and Walter staring at something. I think we're just wiring up the coax. That's why it's kind of dangling. And this extra wire right there, that's just the chunk of wire to the switches, the polarity switches for testing. It's not hooked up to anything, just sitting there. Here's the antennas themselves. You notice, if you imagine you're looking up at it, so imagine that view. You have vertical and horizontal elements. The first one, the UHF, is a 14, so it's got 7 vertical and 7 horizontal. The 70 centimeters of 30, so it's got 15 in each direction. You have a driven element right there. And you notice there's little tabs on it. Those are little metal mounts with set screws, and that's how you adjust the tuning of the antenna. The ones we got from Keith are missing some of the set screws, so I had to find set screws, and then I set them to the factory. We had to build instructions, set them to the factory levels, and we got good enough SWR just to left them. But that's how you tune the antennas. This wiring in here, I lost my beep there. The wiring in there does the matching for the circular polarization. There's another piece to do the coax connection, and there's another one for the polarity switching. I show this picture because there's some folks that will actually run different polarities, and you can run just, depending on how you wire it up and some coax switching, you can run just vertical polarization, you can run just horizontal polarization, or you can run cross polarization, which is different than circular polarization. So you could conceivably do it with these antennas if you want to spend the effort, run a bunch of coax to a bunch of switches, and some people do, but we're not. We're leaving them as they were from the factory. That's right. Also, roughly to scale, that's the comparison between the two antennas, the UHF and the VHF. All right, so now into the meat of the matter, how we'll operate. Try to give a good discussion of actually using the system, but obviously it doesn't make up for a few hours of practice. But hopefully this is the part where you go, hey, I think I want to get involved in this. First is this is going to be, in this part, kind of an overview of how we do stuff. Too bad Bud's not here. He'd enjoy it. We're talking about radio modes. I'm talking about how we actually acquire the satellites. A little bit about how we deal with Doppler shift. I think you know Doppler shift, right? It's the train horn, right? Get the noise changes. Same thing happens in the radios frequencies. And then how we tune the radios or adjust the tuning. I'm going to cover that just a little bit. Again, this is going to be kind of specific to our setup rather than all-encompassing. So hopefully that's somewhat legible. This is taken straight from the AMSAT website. And this is 3 satellites I've worked on this station. Bring this up because this is the information you have to look at if you want to work a satellite. It's got all sorts of good proof on it. And let's start with the first one, SO50 Saudi Sat. It's got the name there. Notice the uplink. It's FM. It's VHF with a tone squelch. Downlink FM, UHF. This is operational. But notice in the notes, it has a 10-minute timer that must be armed. Transmit a 2-second carrier with a different tone. So in our software, if you're running that, you select the first tone, key for 2 seconds, and then you switch to the second tone for all your transmissions. Next one down, P01, PO101. This one, the uplink is UHF, the downlink is VHF, has a different tone, and you can see in the notes that activated by schedule, so it may or may not be operating. You can go to their Twitter account or channel to see if it's operating or not. The last one is what we call a linear or transponder satellite, and I'm really going to cover this really quickly because this is an hour by itself. I'm going to cover it quickly. You notice that the layout for the frequency is a little bit different. So you have an upwind, lower sideband that is 145.935 to 145.995, 60 kilohertz. You have a downlink upper sideband now, 435.610 through 435.670, 60 kilohertz. You notice the label in here, you got a capital V/small u. Uplink, VHF, that's us. Capital V is us, uplink. And then downlink is a small u. Inverting. What does inverting mean? First off, every satellite we're going to operate with this system is inverting. That's the simple part. What that means is if we're over here at 145.935 transmitting, that means we're receiving at 435.670. It's theoretical numbers. As you turn up your transmit frequency, the receive frequency is going down. Rather than mashing together going the same way, so they're going opposite directions. The hard part about these is you have to figure out where you're coming back down, and that's what the transponder means. It's receiving your signal and really piping it down on the other end, but you got to figure out where that is. Where is that matched? Once it's set in software or however you're ready to configure it, it should remain at the same position every time you use the satellite. But you have to find your matching pair, and then from there you can adjust it for Doppler or other signals. That's the other beauty of the sideband linears is you have that whole frequency range to play in. Whereas FM, there is one frequency like a repeater, and the strongest person in blocks everybody else out. In the sideband, you have all that range to play in. CW at the bottom, voice at the top, or whatever you're doing. You're just looking for signals and in multiple conversations within that frequency spectrum.
You especially get a lot of CW signals,
A lot of CW.
as long as you can follow any Doppler moving around.
I'll make a note down here. This satellite has a CW beacon. That's going to come in later on. Last thing I was going to mention, so I've mentioned the radio, our common standard practice is the top is downlink, right? Because the satellite's above us. We're down below, we're the uplink. Well, upper sideband is the satellite, right? So the satellite's transmitting upper sideband. We're transmitting lower sideband. Again, that's just a standard we're using. So how do we track it? I talked about the radio modes, but now how do we track the satellite? The common question I get is people kind of imagine that we lock onto this thing and now we're just going with it. In reality, we are aiming where we think it's going to be based on math. We know where we are, above the center of the earth and that long, and based on Keplerian elements, we know where the satellite should be at a given time. And between those two, all these elements and a little bit of math, you figure out where to point your antenna to see the satellite. Well,
Get accurate time.
and a good time hack. I don't like that much math, so we use software. And the software does all the math. You input where you are, including above, height above sea level, and your lat long. It already knows the radius of the Earth, and it downloads, well, you have to tell it to, but it downloads the Keplerian elements, which are the satellite predictions, and then it aims the antenna based on that data where the satellite should be. And at all points, we're aiming where the satellite should be. We don't know exactly where it's at. We're just predicting it's there based on numbers. This is the software we're using. I mentioned before, it's a Windows software. That's just set up on our computer, and this is how it's set up. If you want to do something else, you're on your own. But I'm going to talk through this software. Oh, by the way, Eric Eichmann, DK1TV, is a German amateur. It's important because all the warnings are in German. Luckily, on the software website, they have a whole list of all the warnings in German and then what that translates to.
They do. It's funny.
I'm going to talk about this first. This is actually, if you look at this right here, this is the main window, main software window, right? This box. All right. The accessory that I'm using is called the Countdown or Countdown Timer, and it's selected by this little button accessory. On our computer, it should always be popped up with the software. You shouldn't have to open it unless somebody fiddles with it. But I find it the most useful part of the whole thing. And I'll zoom in here in a second. So here's a couple zooms. I think you can probably read that pretty good, but I really zoomed in for the heart of seeing. So you can see right here, the top satellite is highlighted. That means that satellite is within view or within that AOS, LOS range. It doesn't mean it necessarily really is, but that's within those numbers, within the range. The first letter I'll talk about, that's the name of the satellite. Because it's highlighted, we know this is the countdown timer to loss of signal. The last number is max elevation. So during its pass, that's the highest it will reach, which is important for your planning. The next one down has a letter F in front of it. That's AO 73. 25 minutes till that one, but look at that max elevation, 1 degree. Yeah, we're never talking about that one. And the last one, C, RS-44, the Russian sat, 31 minutes, and it'll be 17 degrees max E. You'll probably work that one. You notice, I'll show a little bit more highlighting later on, but you notice each satellite is on there one time, and these are just the satellites we are tracking or monitoring, whatever you want to call it. And it just so happens that there's 23 in here. I've only had 23 set. So even though it's 7 hours till this satellite comes, which means some of these satellites will come numerous times before that, it only shows each satellite one time. It's not going to show you each prediction, multiple predictions of one satellite. It's going to show you each pass one time.
One more figure, how many satellites are active?
Those and a few others. So Tom probably have a better number, but as far as the ones we use, it's like 24, 25 maybe, depending on where they're at. Sound about right, Tom?
Yeah, it's about right. They come and go. They watch new ones and then they decay and go away, or
Yep.
die and go away.
Yep.
But
How high is your antenna on the ground?
It's on the roof, so it's
I don't know, but how many feet?
about 50 feet, I think, roughly.
So you got
15
to.
satellites will make passes right now.
So it sounds like you can get things pretty close to the horizon because there's not too many trees real close.
Not much in trees. Fort Worth is a problem. So that's blocking us. Yeah, some buildings. And just south of us, there's a storage thing. And so that blocks us to about 6 or 7 degrees, I think. But for the most part, it should have pretty good signals. So let's go back to that main page again. And I'm going to show you these two blocks. This again has to do with that alphabet we're talking about. So this upper portion and this portion. This Again, let's zoom in. This is what we're actually working. This is satellite we're working. So again, you got a letter right here. You got a name right there. You look down here, A through X, there's 24 slots. I have 23 loaded, which means I could put one more satellite in there to track. There's only one that's highlighted. Well, that's not because I'm tracking it. That's because that one, again, is within that AOS LOS range, which matches that other window I showed you. It's important, right? Because, oh, I want to work this satellite. See, it's highlighted. Well, you got to click on it and make sure it's showing up right there. Otherwise, you're not tracking, you're not working it. Within this window, this is how we basically control the software. So the first one, any of these things, if it's a negative, that means it's turned off, right? It's not on. So the first one is rotor control. So right now, rotor control is not on. Second one is CAT, that's your radio control, that's the auto tuning, mode changes, all that kind of stuff. That is not on. This is automatic satellite change, so it'll cycle through the satellites. This, I think it only works in the transponder satellites, but this puts you into VFO mode. So you can now, instead of the computer changing, locking you into a frequency, you set the frequency you want, and the computer will simply do the Doppler effect on that frequency you selected. So you find a signal, and now it'll just Doppler correct for what you set in. Go ahead.
A little correction, on FM satellites, it's defaulted as turned off,
That's what I thought. Yeah.
but you can turn it on. You have to
Like adjustments.
be able to tune with your radio or with the shifters that are on top of the screen.
Thank you. Let's see. Tone is what I was talking about, right? So that's our CTCSS tone. This tone 0 means no tone at all. Tone 1 means the first one that's stored, and tone 2 is the second one. So the first satellite type got used 2 tones. First tone is what we use to turn on, then tone 2 is what we'd operate on, and that's the nomenclature we're using. These, some are preloaded, some have to be manually loaded. So if there's not a tone set there, but it's supposed to be one, then that means we have to manually adjust the files, essentially. I forget what some of these are. CW puts the radio into CW mode. The M lets you see multiple satellites at one time. It may be too busy, so you may want to turn that off. This is for zooming in. Now, because we're in the widest mode, W5, there's no zoom allowed. I forget what the G is. Some of these have to do with the display, what you're showing. This is which map you want to see, whether it be Earth like this one or a political map. And then finally 2D, this is the 2D map. If you select 3D, you get a globe. So it's user choice. Down here, I already mentioned this is satellites we're using. That when you click on, that's the one we're going to track. Realize the software is not going to attempt to track the satellite until it's close to the AOS. So if it's 45 minutes out, you click it, well, it's not going to move the stuff at all. Once it gets start approaching the AOS, it'll start pre-positioning the satellite so it captures it as soon as it clears the horizon.
Units are on height and range.
What's that?
What units are on height and range?
What are preset? I think it's feet or miles. I'm sorry. I think it's miles, but I don't know. You have to look on that. These are the only numbers I use on this part. This is what the software says where we need to aim these antennas to reach the satellite. So again, you're running the system, you look at the rotor controller, you don't see that, then it should raise a question. You look at the camera, we have cameras on the tower, in case you didn't know, to view this system. If it's not pointing where it should be pointing, it should raise a question. The caveat is, because we have our set to 180, the controller itself sometimes goes, it's a better idea if I just flip it and use it this way. So sometimes it may be exactly inverted, so it'd be like 222 and then 150 degrees is what you see on the rotor. But if you physically look on the camera, it's pointed here. So just understand that sometimes that happens.
Will it always track regular, or does it sometimes have to go around the other way so it doesn't find the cables?
We have the 180 flip. So
Okay.
it only does 360, so south is the limit.
Right.
So it may come back to a flip instead of doing the spin all the way around. So now let's put these two together. Now you see the comparison, right? The highlight highlight, S, S, S. Now you know we're tracking. You can have multiple satellites within the AOS range. So you may have multiple highlighted ones. You may have multiple ones with this blue highlight on it. Just depends on what's happening right at that moment. Now I'm going to talk about the radio itself, how we operate. I already talked about the cat control turns it on and off, but I'm not going to get too far in the weeds on this because some of it I'm still trying to learn. But we have this display up here, and so I brought this in again. This is what the software is setting to the radio. So this is your Doppler corrected frequencies, and you'll see it changing the entire time. If there's no frequency on here, then that means there's none installed or stored for that satellite in the software. So guess what? You got to manually tune yourself. But if it has a frequency in there, then it's stored in there, and it's going to do Doppler corrections. There's some other adjusting knobs, and I haven't used all these things. Some affect linear, some affect FM satellites. But it's to do the corrections, because once you have it locked in to the computer, you can't turn the knob anymore. It overrides. So this is how you tell the software to make the adjustments to fine-tune the frequency. Again, you need to hear yourself come back down through the path. The last bit, there's this button here that says CAT, and it does multiple things for us. One, you can do all your adjustments here. So if you, especially for the linear satellites, to figure out where you are, you make the adjustments here, and then you store it, and then it should stay there from then on. As soon as you bring it up, you should immediately be on the right frequency pair for your radio to work the linear range family adjustment from that point. But also over here, some have multiple frequencies you can play with. They have digital modes or whatever else. You see, this one has regular voice, and then it has a digital mode, and that'll tell the radio to switch to digital, is what that indicates. This satellite, I showed you, this is an RS-44. This is down there, RS-44. That one I said has a CW beacon. Well, I don't see a CW beacon on there. So guess what? I had to adjust the software to add it. So now I can select the beacon, and the radio now will tune to the beacon frequency and track that with Doppler. And I use that to see if the satellite has come up. If it's come up, I can hear beaconing, then that means I can talk to it.
What is the speed? What extends?
I think it has to do with, I thought it had to do with the packet stuff. I don't remember.
It's actually the update speed for the
For the
radio.
radio? Okay.
1 time per second, 5 times per second, or 10 times per second. So, for some people just leave it at 1 time per second. You can hear their signal back. I like 5.
So now we get into the teaser part. This is the future things we're working on, trying to get done. So I'm going to talk about remote operation and then the ISSD TV download. So remote operation, as soon as we started working on this, and this is because the club got spoiled because they built a remote system for HF, they go, hey, when are we going to have this remote? It's a lot more complex than that. The biggest reason is the rotor is continually turning, so the software has to talk to the rotor. So that's the biggest issue, is the fact the software has to talk to the rotor through the computer, right? It's physically attached to the computer. I think so I'm playing with it. I think it's going to be limited to FM satellites. I've been using some software and just can't quite get the sideband stuff to work correctly, but it's still really early stages. It's going to require a lot of user training, and the user is going to have to be well versed in the software because it's a lot of manual setup on their end to make it work. And finally, if you're having problems with the radio software, we're running an ICOM radio. The ICOM radio software is the worst of all of them. It does not have any duplex at all. There's 2 other softwares I've been using. One's an open source. It can sort of do duplex, but it's it's in the early beta stages, and the writer doesn't even do satellites, so there's no idea how that works. The other one I've used is called Win4ICOM. It's written by, I got the notes at the end. It's written by this guy, I think it's in Europe. It actually works pretty well. It does full duplex. It shows the scope, the audio scope, all that kind of thing. And they constantly do updates to it. However, there's a bit of a lag on what your display shows that the radio is doing. So I'm not 100% sure if when you go transmit or not, if there's a lag in the actual transmission or if that's just a visual lag on the display. So, but I think that's probably our best bet. The issue is it's $60. I don't know what the licensing is, if the club can buy a license, nobody can use it. I have no idea. The ICOM one's over $100. It doesn't work at all. Now, if you already have the ICOM software, the Win4 ICOM will use the ICOM server software, so they'll talk directly to our radio rather than needing the intermediary software. That's the only advantage of it. So here's an example. This is me operating in my house. Actually, I have a third screen on with another tracking program. I'm running simultaneously. But I'm just showing you this because this is our software. That's Win4ICOM, showing the full duplex setup. Right here, I'm using the ICOM server software directly connected to the radio. And then here I'm using SAT-PC32, using virtual COM ports through our VPN to the club. That seems to work pretty good, but it's the radio part that's having issues. All right, the next teaser is the ISS DATV project, or ham TV. In 2014, the Eris sent up a transmitter, actually built in Italy, to transmit full-time high-speed video from the ISS. In 2018, like I said, the transmitter failed, and they sent it down to Earth in 2019. It's been lounging in Italy all during the drama, and it finally got shipped back to the U.S. And Randy Berger and his team worked on it and tweaked it, got it retested, had to build a filter pack for it because it was jamming every single frequency all at once. Got all that, got it all approved, and got set up on the resupply in April. We don't know what the schedule is for them getting it wired in, but at least it's on the ISS right now. It is a 2.395 gigahertz downlink. It is one way, or it's receive only. Circular polarized signal, and it's using QPSQ, and I can't remember what that does, but Mark was working on that part of it. Here's what the normal setup to receive would be: if some kind of reflecting dish, some kind of feed, we call it. It's, for our concern, the whole thing's an antenna, but they call it the feed. You got some kind of low noise amplifier. In our case, it's a 23 dB transverter, so it takes that 2.4 gigahertz signal and drops down to 900. 900, I think.
Yeah.
Drops down 900, and then it sends it over straight coax to a satellite receiver box. In our case, is one created by the Eris team. And then ours will plug right directly to the computer so we can feed the video over. This is ours in the test bed in progress. This is the tuner, which is this thing. Sorry, you guys in the live feed aren't going to see it, but Eris MTV mini tuner in weird French lettering. Keith bought this. It was $250 when he bought it. These don't exist anymore because the receiver part, the antenna tuner part, aren't made. Not shown is the low noise amplifier, which is right here. It's 23 dB, made by Kuhn Electronics. I think it's a German company. They don't give those away either, but I think it's under $100. Sure. And then you can see that in this picture, I zoom in here, we're actually transmitting a video signal from this. We're testing with this, transmitting a video signal, and you can see, and this is the QPSQ, that's what, yeah, that thing. It gives these 4 dots, right? So you get the 4 corner posts. It's compression algorithm, I don't know.
That's voice modulated.
There you go, modulation.
Those four bright spots on the bottom screen there, the signal itself has two components to it, and the relationship of those two components can move by 90 degrees around that spectrum. And it's based on the phase difference between those two signals.
Quadrature nation king.
Yeah, the quadrature implies the 4 dots.
But we got to work.
So
And Mark,
that's our ISS in a box.
yeah, I sent the box. Mark kind of took the lead on this part because he's got a little bit, maybe had a little bit of background and this kind of thing, maybe. That's it for my briefing. Any questions? Before I answer questions, this box right here is the transmitter. It's made by an Italian company. I can't remember what it was. Made by an Italian company. Samantha Cristoforetti there represents Italy for the European Space Agency. She was the first female astronaut for the European Space Agency. She held the record for women in space until the record was broken a year ago. And she was my student as lieutenant when she went through pod training as the Italian Air Force. She's smarter than me. I didn't teach her anything. So what questions do you have that Tom can answer?
You guys have done it.
Does it work?
Oh yeah,
Oh, yeah.
those three satellites I showed you. I've worked all those a few times. I haven't worked the ISS yet, although when I was testing the remote system, I didn't have the transmit part set up yet, and I listened to the audio all the way across. And in fact, we're talking about where it drops out. The antennas were pointing straight at the storage building next door at 0 elevation. They'll still get a strong signal as this ISS is passing over Mexico. But that's the ISS. It's a different breed. It's high power, wide range. What questions?
I really want to appreciate what Mike's done. You can actually do the same thing with a hand talkie and a handheld antenna. The only problem is you've got to trace the satellite that goes across the sky. You have to turn the antenna by hand to match the phase rotation, and you have to adjust the frequency on your radio by hand while you're doing that to the Doppler effect, all while trying to talk on the radio. And you can do it. But it's just, it's interesting to use real.
It's much easier with high dB gain antennas and a tracking system. Like I said, the plan is, as I go through all the satellites and get contacts and make sure everything's working, the FM one seems to lock right in right away, with no adjustments. The sideband ones I've had to fiddle with. But
Everyone is unique. That's
Yeah.
They all have quirks. And it's figuring out the quirks and how to deal with the quirks.
what questions y'all have? When can you go? Anytime. I got keys to the place, so
I got a question.
shoot.
Hey, Mike.
When did you
Hang on.
start? When did you start?
Mike, can you hear me?
Hang on, Anthony.
When did you start the project? And when did you get to this? It's probably never finished. But when did you get to the current status? How long did it take?
So during COVID, I was bored. And when Keith had brought this up, I volunteered to help him with it. But when the transmitter stopped working, he was no longer in a hurry to do it. Like I said, he passed it next year, so our metro was gone. So I went and eventually, like I said, got the remote system working. I was like, okay, what's the next job I can work on? And I went through and just inventoried everything we had in our equipment racks and everywhere else to see what we had. And I broke it all down to satellite versus non-satellite stuff. And I figured out everything we had, and it was like, So this is still during COVID. This is like maybe 21, maybe. I can't think exactly what year it was. But once I had all the pieces and parts that we had as a club, I started trying to find who has a system like this. I can copy what they did. I mean, we have our portable unit. I know how to build that. But this is different, because this has to sit up there without anybody playing with it for long periods of time. So I just searched Google for all these different satellite setups and all this other thing. And I found Fred Kemmer up there. At that time, it was just the club. Natasha, New England, yeah.
New Hampshire.
Yeah, New Hampshire club. He was the president. But I found his setup, and he had all the exact same things. So he had eventually upgraded to bigger antennas. but he's got the same brand antennas, the same rotor controller, and he had the newer icon, we had the older icon, but same preamps. And so I just sent a message, said, hey, we're building the system, we're trying to figure out stuff. Can you give me a little, explain your system? He says, let's do a Zoom meeting. So it's scheduled a Zoom meeting, and he talked for 2 hours explaining everything I need to do, including how to build the thing, which was the first thing you want to do is build it on ground level and test it for weeks to make sure it all works. Because once it's up, you're not going to want to fiddle with it. And that was the best information I got. But basically, I copied all his stuff. So that picture, the box, the fan box, that's his. That's on his tower. I just copied it because, hey, why reinvent the wheel?
So is 120, how is the rotor, where's the rotor controller the power supply? Is it in the building or is it up on top?
It just runs off the green heron.
So you just have wires running up to
Yeah.
the motors?
Yep. Yeah, the green heron powers it.
So there's no power except for, you're powering the preamp, but that's all through the.
Over coax, exactly. Not with any power up there.
So there's no power.
Exactly. It's a short run, so we can get away with it. The problem is if you have real long runs, like at a university or something, you may have enough power drop that you actually need to run power to the location and then switch it remotely. But because we have such a short run, we can get away with just powering stuff directly.
You know, the ground for lightning.
Also, I was saying, up in the doghouse, that's our entry to the outside world. So we've got surge protectors, alpha deltas for the coax, and then we've got I think it's a Orton or Martin surge protector for the rotor controller itself. Organ systems.
A few years ago in AmFest, a portable unit, had the SWAT meeting we have in January that same year, Randy did couplers, I can do some of the calculations to get you there. So 2 different years now, I can set up a portable unit.
For field day.
Out of AmFest.
Field day.
For field day, yeah. And then, so once we got that done, the real problem, getting it done here, and it actually became a much bigger project because redoing the light direction stuff for the satellite, we also wanted to do it for all of our other antennas at the same time. So it was actually a complete rewire of the system and grounding of the building. And Sam did a bunch of research on grounding and what we needed to do for grounding and running the cables and where our entry points. And then there's been a big project the whole time.
I think that last part of your question, we got it operational last fall sometime. The summer was so hot, it couldn't work on it all. But last fall, it was fully operational, so it's been operational since then. So it took from
3 or 4 year project.
yeah. But again, Ray Hood helped a little bit, but he's got a totally different system than we had. So Fred did, like I said, copied everything. So I'd say he did most of the work, even though not directly, just that big mentoring session, and emails and stuff. And Ray just for some of the radio stuff. And then once we got it built, he went up and looked at it and did a pretty good job. So I felt pretty good about that. But using the system, Ray taught me that, just working with him a field day. But yeah, it took a bit. It was a big project. And one of those things like, you can't redo it. You can't make the coax longer. So there's a bunch of different pieces that had to be designed and planned and redesigned and replanned because once you pull the trigger, that's it. Had a bunch of help. Walter Mike Query did a bunch of work on it, and all the folks running coax and everything else.
Anthony had a question.
I'm sorry, Anthony, go ahead.
Whether you're on Zoom or in person, I want to clap and say thank you to Mike for his wonderful presentation. Mike, I do have one question regarding operating at the clubhouse versus operating at field day that we normal. Can you operate the linear satellites when we operate during field day at the park, or is that strictly just FM birds?
Yes, we can operate the linears also.
Okay, well, thank you.
Well, I got Randy Berger on there because we didn't understand the ham TV part of it. And we read through a bunch of stuff and just couldn't wrap our head around it. And I knew we needed to build a test bed. We could build a receiver, but we don't know if it's working unless we have someone to test it. And, Randy, right? Real busy, a lot of stuff going on. He just said basically one word. He said two things. He said Adam Pluto, and he said QO100. QO100 is a big satellite, geosynchronous. It's sitting over Africa. It's run by Emirates, I think. I can't remember who it is, but somewhere there. But it has a ride-along amateur radio component of it, which is it was 10 gigahertz up, 2 gigahertz down. It's running ham TV, so they can do high-speed TV via amateur radio or amateur equipment through that system. Well, the same exact technology is what is pretty much the standard for all the DATV, ham TV stuff. So once I ground down to that and found out what they're using in software and stuff, that made the rest of this a whole lot easier. Not really easy, but a whole lot easier.